So today we're going to take a look at the double angle identities. This is the last section of the trigonometry section. And quite often when people see a double angle identity like sine of 2x, they think that you can just take the 2 out front and make this 2 sine x. No. But it doesn't work. So
I knew that one.
We want to just choose a number x to show that this doesn't work. So we can choose any random angle. 90 degrees. Let's see if it works. So let's try 90 degrees. Okay, so instead of x, we'll put 90. So sine of 2 times 90 is sine of 180, which if we look at our xy axis, that's over here. We're looking for the y-coordinate. The y-coordinate is sine. Sine of 180 is 0. Now, 2 sine 90 is, well, let's see, sine 90 degrees is up here. The y-coordinate at that point is 1. Times 2 is 2. 2 does not equal 0. This does not work when x is 90 degrees. Okay, so there's a numerical argument to show that it doesn't work. And we can also do this with a graphical argument. So do you know what the 2 does when it's inside with the x? It compresses it horizontally. That's right. So it makes it half as wide. And what about when the 2's outside of the function? It's a vertical expansion. So a vertical expansion times 2 is not the same as a horizontal compression times 2. We can show that by graphing. So let's graph y equals cos 2x and y equals 2 cos x to show that these graphs are actually not the same. So take out a graphing calculator, make sure you're in radian mode. Cos 2x should be a compression. 2 cos x should be an expansion. And I'll zoom trig number 7. So there's my cos 2x. I can fit 2 waves from 0 to 2 pi. And here's my 2 cos x. I can make one of them darker so that it's more clear. Cos 2x is compressed. 2 cos x is expanded so that it's 2 times higher. So cosine 2x still starts at a maximum, but this time instead of fitting 1 wave, we can fit 2 waves from 0 to 2 pi. And 2 waves from 0 to negative 2 pi. And 2 cosine x goes all the way up to 2, down to negative 2, up to 2 again. Okay, so those 2 graphs are not the same. Couple other things that are not the same. Sine squared x and sine x squared. So when you have the squared right after the sine, what that means is that the whole sine x function is squared. When you have the squared right after the x, it means that just the x is squared. So let's use an example of an angle to show that those 2 are not the same. Let's go 60 degrees. So sine of 60 degrees is, that's my 1, 2, 3 triangle. It's root 3 over 2. And then if I take root 3 over 2 and square it, I get 3 over 4. Now what about sine of 60 squared? 60 times 60, sine of 3600. That was a really good choice. That's 10 times around, and we're going to end up right back at 0 again. So sine of 3600 is 0. The y-coordinate is 0. 0 is not equal to 3 over 4. So this is not true for 60 degrees. And we can try this also on the graphing calculator. So let's graph cosine x squared and cosine x squared. It's kind of fun to think about what will this look like before we even graph it. We didn't talk about what happens when you square an angle. We'll do the standard trig window from -4 to 4 for y, -2 pi to 2 pi. Okay, so for the first graph, when you square a number, it makes it positive. So all the negatives became whoa!
Oh, that poor graph.
Oh, my cosine x squared is totally obliterated. I'm going to turn that guy off for a second so I can draw my nice, I love this cosine x squared. All the negative, it's like a bouncy ball. All the negative values became positive. Whee! And the period also changed. And the period actually became half as big at the same time. Whereas my cosine x squared is really weird. Craziness, slowly becoming craziness again. Yeah. So those are definitely not the same graph. So now let's discover the formulas for sine of 2x, what it really should be. So here we go. Sine of 2x is the same as sine of x plus x. So now we can use the expression for adding two sines. When you add two sines, you get sine cos plus cosine. And we put in the first angle and the second angle. So sine x cos x plus cos x sine x. Which is really like AB plus BA. I'll give you all of the addition formulas and the double angle formulas. You got to know the tan one. The tan one will not be given. So this is 2 sine x cos x. Okay, so pause the video and go back to your expressions for cosine and tangent and see if you can derive the expressions for double angle identities for cosine and tangent. So in order to derive the double angle identity for cosine from the addition identity, we're just going to use the formula for cosine, which is cos cos, sine sine, and the sign in the middle changes. Then we put in first angle, second angle. So we get cos x minus sine x sine x. Cos x times cos x is just another way of saying cos x squared. Sine x times sine x is another way of saying sine x squared. Okay, that formula will be given to you on the formula sheet. Is that equal to 1? Why not?
You have to add.
They have to add in order to equal 1. If you subtract them, then it doesn't equal 1. Now the tan x formula, well, you won't need to be able to derive this one. Remember that tangent is just sine over cos. So here's the formula for a double angle for tangent, tan x, tan y. So now if both of the angles are the same, we're just going to put x's instead of the y's. And on the top we get 2 tan x's, and on the bottom we get 1 minus tan x squared. So that's a formula that will not be given to you. So you can use the fact that sine squared plus cos squared equals 1 to rewrite the cosine 2x formula. So instead of cosine squared x, you could solve this equation for cosine squared x. So let's just get cosine squared on one side by itself. So move the sine squared x to the other side by minusing it. So you get 1 minus sine squared x. And let's just take that thing and put it into the equation instead of cosine squared. So we'll have 1 minus sine squared minus sine squared. So that's the same as 1 minus 2 sine squared x's. So there's another formula for cos 2x. Okay, so they have one formula that has cos squared minus sine squared. There's another formula that just has sine squared. Can you make a formula that only uses cos squared? Pause the video and try it. So in order to get the very last formula for cosine 2x, instead of substituting for the cosine squared, let's substitute the sine squared. So let's solve the sine squared plus cos squared equals 1. Instead of getting cos squared by itself, let's get sine squared by itself by moving the cos squared to the other side. And then taking that 1 minus cos squared and putting it in instead of sine squared. So you get another formula that says cosine 2x is the same as cos squared minus 1 minus cos squared x. So the minus minus is going to change that to a positive. So we get 2 cos squared x terms minus 1. So when you move that minus sign in, the second cosine squared will become positive. So that's the last formula for the cosine double angle identity. So now turn over to the other side. And we'll put this into practice. So we're given an identity, which means that this is true for all x's. So let's check that identity using the number pi over 3. So is sine of 2 pi over 3 over 1 minus cosine 2 pi over 3 equal to cotangent of pi over 3? Now let's just use the calculator on this one. You can do this one in your head because they're all nice, perfect numbers, special angles. Well, let's do this one on the calculator. Sine of 2 pi over 3. And put brackets around the denominator. 1 minus cosine 2 pi over 3 is 0.577. How do I do cotangent of pi over 3? 1 over tangent. 1 divided by tangent pi over 3. Hopefully I get the same answer. Yay! 0.577. Do you know what that is as an exact number? Root 3 over 3, or 1 over root 3. Yes. Now let's graph both sides and see if they look the same. So this is one way to graphically show that an identity is true. If you graph both sides and they both look the same, then we have an identity. So let's make one of them dark. Here is sine 2x over 1 minus cos 2x. Here comes cotangent. It's not quite the same, actually, on my calculator. One of them drew the asymptotes, one of them didn't. That was very strange. So sine 2x over 1 minus cos 2x is exactly the same as cotangent x. The graph is these things. 4 of these things fit from negative 2 pi to 2 pi. And now let's prove it. So maybe you need another piece of paper to prove it. Or you can fit it just under here. So for the right-hand side, we need to change cotangent into something that uses cosine and sine only. Cos x over sine x. Anytime that you're trying to do a proof, and you see that there's double angles, so like 2x inside of a cosine or sine, always change it using one of the formulas for the double angles. So for sine 2x, we only have one option. We can only choose this one. So we're going to change the sine 2x to 2 sine x cos x. But for cosine 2x, there's 3 different choices. We have 2 cos squared x minus 1, 1 minus 2 cos squared x, 2 sine squared x, and cos squared minus sine squared. So there's a really clear choice with these type of problems. You can always get to the right answer, but it might take you more steps. There's one choice here that's going to get us to the right answer in the least number of steps. Here we've got 1 minus this thing. So we want to choose one of them that's going to have a 1 that can cancel off. So we want 1 minus 2 sine squared x. We want to use this one because the 1s are going to cancel. Because 1 minus 1 will be 0. Okay? If we did 1 minus negative 1, then we get 2. That wouldn't work. Okay, so this is the easiest way, is if we've got 1 minus something, we're going to use the one that has positive 1. 1 minus 2 sine squared x. Because what happens is that when the negative sign goes in, the 1s will cancel, leaving us with 2 sine x cos x over 2 sine squared x. So the 2's cancel, the sines cancel, and you're done. So choosing the right version of the cosine can really help simplify your steps. Now this is what your homework will be like for today. Basically it's just like what we did last class, just trying to match. So you're looking for something that's cos squared minus sine squared. You can see cos squared x minus sine squared x is the same as cosine of 2x, where x is just the value of the angle. So cosine of 2 times 15 is cosine 30, which is 3 over 2. Now you try the next two. Pause the video and see if you can simplify those. So the tan 1 matches the tan 2x pattern perfectly. But instead of x, we put the angle pi over 12. So this is tan of 2 pi over 12, which is the same as tan of pi over 6. So tan of 30 degrees, which is opposite over adjacent, 1 over root 3. Good job.
Nailed it.
Yay! Now, 2 minus 4 sine squared theta doesn't match any of the patterns. It's supposed to be 1 minus 2 sine squared theta. So it's 2 times too big. So maybe if we factor out a 2, then it will match. So we can take out a 2, and then we can change it to cosine of 2x. So instead of x, I'm going to put 7 pi over 12. So this is cosine of 2 times 7 pi over 12, which is cosine of 7 pi over 6. So where is that? 1, 2, 3, 4, 5, 6, 7. That's down here. It's my 1, 2, 3 triangle. 1, 2, root 3. Cosine is adjacent over hypotenuse, so negative root 3 over 2. So this is 2 times negative root 3 over 2, which is negative root 3.
Oh.
This is, again, one of the hardest questions from your upcoming test. So, getting this, you're on a roll. Yes. So if you want to find out cosine of 2 theta, anytime that you have a double angle, always break it up using one of the formulas. So in this question, we're given the value of sine. So we've got 3 choices for which cosine 2 theta formula we want to use. Probably a smart idea to use the one that has sines in it. And only sines. Why not? So let's change this to 1 minus 2 sine squared theta, which is really the same as 1 minus sine theta squared. So sine theta, it tells us in the question that sine theta is the same as 3 over 5. So instead of sine theta, I can actually write the number 3 over 5. So now 3 squared is 9, 5 squared is 25. So this is 25 over 25 minus 9 over 25, aka 16 over 25. That's it. So it looks like a really complicated question. Yeah.
It says it's 1 minus 2 sine squared.
Oh, I'm sorry. I forgot the 2. Let me fix this. So it's 7 out of 25. Otherwise, it would be cos squared theta instead of cos 2 theta. So the second question is asking us to find the value of sine 2 theta. Now, sine 2 theta only has one option. You're always going to replace this with 2 sine theta cos theta. Now, unfortunately, we need sine theta and we need cos theta, but we only have tan theta. That's not so helpful. So I'm going to actually have to draw out that picture. So tan theta is negative 2 over 3. Do you remember what that is in terms of x's and y's and r's? Y over x. So I'm drawing that one in quadrant 4, which is down here. So if I draw that, the x coordinate needs to be 3, and the y coordinate needs to be 2. So that means that y is going to be negative. So y is negative, x is positive. And then I can find the hypotenuse just by doing x squared plus y squared equals r squared. So 2 squared plus 3, or I should do 3 squared plus 2 squared is 4 plus 9, 13. That's right. So r is the square root of 13. So sine would be opposite over hypotenuse, negative 2 over root 13. And cosine would be adjacent over hypotenuse. 3 over root 13. So now I can multiply 2 times 2 times 3 is 12. Root 13 times root 13 is 13. And that's the solution. Any questions? So, very last page. More proofs. So for the first proof, instead of tangents, we're going to write sines over cosines. Now tan squared is the same as sine squared over cos squared. So we want to try to get rid of the denominators. So we're going to multiply everything on the top and the bottom by the lowest common denominator, which happens to be cos squared theta. And when we do that, on the top, one of the cosines will cancel, leaving us with 2 sine theta cos theta. And on the bottom, the first term just becomes cos squared theta, and on the second term, both of them cancel, leaving sine squared theta. Now, sine squared plus cos squared is 1, so this is 2 sine theta cos theta over 1, which is the same as sine 2 theta. Beautiful. For the second proof, any time that you see a double angle, always change this. We don't have any options for sine 2x. There's only one equation that works. But for cosine 2x, we have 3 options. So it doesn't matter which of the 3 options you choose. You're always going to be able to prove it. It's just which one's going to get you to answer the quickest. So because we already have 1 plus, I want to choose one of the equations that has a negative 1 so that the 1's can cancel. So look at my 3 equations, and I see the 1 on the bottom. If I make cos 2 theta into 2 cos squared theta minus 1, then the 1's can cancel, and that'll be the fastest way to prove it. So the 2's cancel, one of the cosines cancel, leaving sine over cos, which is the same as tangent. Now we're totally switching gears for the last 2 examples. The last 2 examples are no longer identities. This is now back to what we started with. In the very, very, very beginning of this unit, we were solving equations. These are not always true for every x. There's only certain values of theta where this is true. Now it says write it in terms of cosine theta only, and you look at the equation and you're like, wait a second, this is already cosine theta only. There's no sines. What are they talking about? Cosine 2 theta does not count as cosine theta. It's a totally different function. It has a totally different period. So we need to change the cosine 2 theta so it only has cosine theta. So let's change this to 2 cos squared theta minus 1. Okay. I am going to let cosine theta be the letter a. This is 2a minus 1, 2a squared minus 1 equals a minus 1. Do you remember what to do?
Add 1.
Okay. Gather all the terms together on one side. So I'm going to make one side equal to 0. So the 1's actually all cancel off. Get 2a squared minus a equals 0. Then, factor. Common factor is a, not the 2. The 2 actually stays inside. What do I need in the bracket there still? 1. It's got 2 terms. So there's 2 possibilities. Either a is 0 or a is 1/2. So now that I've solved it for A, I can look back at what I let A be. So I said A was cosine theta. So now I'm going to put my cosine theta back again. Either cosine is 0 or cosine is 1/2, which is x over r. So let me draw my little triangle, unit circle. When is cosine theta equal to 0? That's when x is 0. How many degrees? 90 degrees. X is 0 at 90. Is there another answer? 270. You can also see that by graphing out the graph of cosine theta. And it looks like this, and it crosses 0 at 2 points, 90 and 270. There's 2 ways that you can come to that answer. Now, x over r. Cosine is positive 1 over 2. So that's my 1, 2, 3 triangle. I want x to be the short side of the triangle. So that's over here, exaggerated. 1, 2, root 3. So that looks like 1 30 degrees, 2 30-degree angles, 60 degrees. Is there another possibility? Quadrant number 4. You can also draw that triangle down here. And how many degrees is that one? 360 less than 360. So there's 60 or 300. So there's my 4 answers for theta. Okay, last example. We've got cosine squared and sine in one equation. This is a problem. We can't solve it. We have to have it all written in terms of either cosine or sine. So do you know which one I should use, cosine or sine? Tangent. Do you think it would be easier to change the first one or the second one?
The first one.
The first one.
Oh, but
It's not cosine 2x. It's cosine squared x. So I can't use the one of the 3 that we developed today. Got to use Old Faithful. My favorite.
oh, 1.
That's right. Cos squared plus sine squared equals 1. The most useful trig formula. So I'm going to solve this for cosine squared by moving the sine to the other side. And then I'll take that and plug it in to my cosine squared. So I'll put in 1 minus sine squared. And this is kind of like mathematical gymnastics here. Of course, if I'm lazy, I would just graph it and find out where it crosses the x-axis. And then at least I know what my answers are. And I could just work backwards from there. So now I'm going to expand. So 2 minus 2 sine squared x minus 3 sine x minus 3 is 0. Now I'll let sine x equal my favorite letter, C, because it stands for my first name. So 2 minus 2, you can choose whatever letter you want. Choose your favorite letter. Could even be the letter P in Greek, although that might get confused with the constant. So 2 minus 3 is negative 1. I really don't like having negative terms. So I'm going to take all those terms and move them over to the right side instead. So they all become positive. Now I'm going to factor it using the Chinese method. So the Chinese method tells me find 2 numbers that multiply to 2. 2 times 1. Then find 2 numbers that multiply to 1. 1 times 1. And then when I go across, 2 times 1 plus 1 times 1 should equal the middle number. So then the first line is my first factor, and the second line is my second factor. So I get 2 possible answers. Either C is -1 or C is -1/2. So now I can put back the sine thetas. And now I can think of it in terms of y over r. So again, I'm looking at a 1, 2, 3 triangle. So y is the short side of the triangle. Y is -1, so it'll be the short side. That can happen in 2 places. 1, 2, 3, root 3. And when sine is -1, that's when the y coordinate is -1. There's only one place where that happens. 270 degrees. But I think that this one's asking me for the answer in radians, because they told me I wanted to get the answers from 0 to 2 pi. So I actually like this better, because now I can count 1, 2, 3, 4, 5, 6, 7 pi over 6, 8, 9, 10, 11 pi over 6, and 1, 2, 3 pi over 2s. So there's my 3 answers for theta. Your homework is page 300, just numbers 1 and 4 and 5.